Hello everybody. In the last class we were discussing at length on the topic of the rotating magnetic field generation in the induction motor. How is the rotating magnetic field generated? So we saw that if we apply three-phase voltage or three-phase source to the stator coils, then the three-phase currents in the stator coils, which are 120 degrees spaced apart in the time axis, are applied to the three coils, the poles in the stator, which are placed mechanically at 120 degrees apart. So this causes the resultant flux or the MMF to rotate in the air gap or rotate in space, and this rotation causes a differential relative difference in the speed between this rotating flux and the rotor conductors. This induces a voltage in the rotor conductors. Of course, the rotor conductors in the squirrel cage are shorted, which means a huge current flows in the rotor conductors. This current in the rotor conductors interacts with the flux which is produced in the air gap and provides a force which makes the rotor conductor move to try and catch up with the field. So all the accumulated forces of all the rotor conductors on the circumference of the rotor add up and you get a massive torque which makes the rotor to move. So this is the principle of the operation of the induction motor. But we saw that as the rotor, let us say the rotor speed catches up with the speed at which the flux is rotating, which means there is no relative difference in speed between the rotor conductor and the flux, which means the flux will not cut the rotor conductors, and as a result there is no induced voltage in the rotor conductors and thereby no induced current. If there is no induced current, then the Lorentz force F, which is equal to BIL, I being 0, there is no force on the rotor conductors and therefore the rotor will tend to lag because of the frictions of the bearings. And therefore, there will always be a slight difference in the speeds of the rotor shaft and the rotating magnetic field. The speed at which the magnetic field rotates is called the synchronous speed, and the speed at which the rotor rotates is called the mechanical speed or the shaft speed, and the mechanical speed is always going to be slightly lesser than the synchronous speed by a small amount, and that is called the slip. So we saw what the slip is also and how it is defined mathematically. Then we also saw one interesting phenomena, that is, if we add more poles per phase, if we had just two poles per phase or one pole pair per phase, then for every cycle of the currents which are applied in the coil, there is one cycle of rotation or one revolution. If we add one more pole pair or two more poles, which means four poles or two pole pairs, then for every cycle of rotation the magnetic flux or the MMF has rotated 180 degrees, which means two cycles are needed for the complete rotation or one revolution. So if there is two pole pairs, you need two cycles. If there is three pole pairs, you need three cycles, so on. So we established the relationship, that is, the synchronous frequency is given by 120 Fs stator frequency divided, that is stator current frequency, divided by the number of poles, or 60 Fs by number of pole pairs, or omega in radians per second by number of pole pairs, or 2 omega, where omega is in radians per second stator frequency, divided by number of poles. So these are the various relationships that we try to establish in the last class, and we continue from there. Now, when the rotating magnetic field is moving in the air gap and cutting the rotor conductors, initially the rotor is at standstill. That is, it is not moving. So the relative speed between the rotor and the rotating magnetic field will be the frequency of the stator itself. So suppose we have standstill condition. So under standstill condition, let me put it in both the RPM equation and the radians per second equation. Nm is the mechanical speed in RPM, which is equal to 0. Omega m is the mechanical angular speed in radians per second, which is equal to 0. Ns is equal to 120 Fs by P, the number of poles, and omega s is equal to omega actual, that is applied to the stator, divided by the number of pole pairs, or 2 omega actual by number of poles. So what happens to the slip, which is equal to ns minus nm by ns, which is equal to 1. Same here, omega s minus omega m by omega s, which is equal to 1, because omega m is 0 under standstill condition. So when the slip s is equal to 1, the relative motion between the rotor conductors and the rotating flux is maximum, and that is ns itself, and therefore the induced voltage in the rotor conductor is going to be very high, but the rotor is short circuited, and therefore instead there is going to be a large current till the motor picks up speed and the relative speed between the mechanical speed and the synchronous speed reduces to a smaller value. Now if we say that ER is the voltage induced in the rotor if rotor windings are open circuited. Means in the case of the squirrel cage motor, the end shorting rings, you open them, then the rotor windings are open circuited. Or in the case of the wound rotor, the slip rings, the brushes are removed from the slip rings and the slip ring portions are opened out. That is open circuited. So which means the relative motion between the flux and the rotor conductor is going to induce a voltage. Now there is no current flow because it is open circuited. So you have the rotor voltage under open circuit condition, and this is at standstill. Okay, and under any other slip, the rotor voltage is equal to S times the rotor voltage when it had been open circuited at standstill. This is standstill. It is slip times. The induced voltage is slip times, linearly proportional to the slip. And what about the frequency? When the rotor is at standstill, the rotating magnetic field has a frequency of, let us say, omega s. Then the relative speed is also omega s, and then the induced currents in the rotor has a frequency of omega s. Now as the rotor is catching up with the rotating field, let us say it is rotating at omega m, but the relative difference in speed is only omega s minus omega m, and therefore the currents in the rotor will have that frequency, which is omega s minus omega m. That is the slip frequency. So therefore, if Fr is the rotor frequency, then it is S times the stator frequency. So these two relationship are important to remember. The rotor voltage and frequency relationship with respect to the slip. Now let us clarify this speed, slip and the rotor frequency with a small example that I have here worked out. Let us take a 4-pole 3-phase 50 hertz induction motor. Now for this induction motor, calculate the frequency of the rotor currents, meaning calculate Fr for the following conditions. 1. At standstill, meaning the rotor shaft is not moving. Second, motor is running at 500 rpm in same direction as the field. Third, motor is running at 500 rpm, however in opposite direction as the field rotates. And fourthly, what is the condition of the motor is running at 2000 rpm in same direction as field. Same direction as the field. Let us understand the operation of the motor under these four conditions. So we say it is a 4-pole 3-phase 50 hertz induction motor. So first let us find out the synchronous frequency. Let us find out the synchronous frequency. NOS Now we know that the synchronous speed ns is equal to 120 f stator by number of poles p, which is 120 into 50 hertz is the stator frequency by 4 poles that we have said, and this is 1500 rpm. This is the synchronous frequency. So now if we take case 1, this is at standstill, Now under standstill condition, what is nm? Nm is 0 rpm. What is slip? Slip S is equal to ns minus nm by ns, and that is equal to 1500 minus 0 by 1500, and that is equal to 1. Slip is equal to 1. So what is the rotor frequency Fr, which is equal to S times slip times the stator frequency, which is 1 into 50 hertz, which is equal to 50 hertz. So the rotor currents are having a frequency of 50 hertz at standstill. Now let us take case 2. Now here we said that motor turns at 500 rpm in the same direction as the field. So this is the second condition. Now here, what is the slip? Now slip is 1500 rpm minus 500 rpm divided by 1500 rpm. So this is 1000 by 1500, and this gives you a value of 2 by 3. So the slip is having a value of 2 by 3, or which is equal to 0.66. Now what is the rotor frequency? Fr, which is equal to slip times the stator frequency Fs, which is 2 by 3 into 50, and that is 33.33 hertz. This is at an RPM, 500 RPM, the same direction as the field. This means that the motor is motoring in its regular manner. The speed is lesser than the synchronous speed. Now the third condition is slightly different. Now the motor turns at 500 RPM but in opposite direction. In opposite direction as the field, with respect to the field. So this means the speed is negative. So we take, let's say, counterclockwise as positive, clockwise as negative. So if it is rotating, if the rotating magnetic field is rotating in a counterclockwise or anti-clockwise direction, which is considered as positive by convention, then let us say the motor is rotating, shaft is rotating in clockwise direction, then it is minus, and therefore we have the slip now, which is 1500 RPM minus of minus 500 RPM. See the negative sign here. This is because of the reversal of the direction, 1500 RPM. So this gives you 2000 by 1500, which is 4 by 5. sorry, 4 by 3. This is 4 by 3, which is equal to 1.33. So you see the slip is greater than 1. So if the slip is greater than 1, see slip is equal to 1 is there is no speed, motor is at standstill condition. When the slip is less than 1, it is motoring. When the slip is greater than 1, it is braking. So this, whenever you have a slip which is greater than 1, it is braking operation. And whenever the slip is between 0 and 1, this is normal motoring operation. So let us look at the fourth condition. So the fourth condition, motor is rotating in the anti-clockwise direction itself along the field. Motor rotates along field direction at 2000 RPM. So we see here NS is 1500 RPM. NM, the speed of the shaft, is 2000 RPM. This means that the mechanical shaft speed is greater than the synchronous speed. So what happens to the slip? The slip goes negative. NS minus NM by NS is now 1500 minus 2000 by 1500, which is minus 500 by 1500, which is minus 1 by 3, which is equal to minus 0.33. Now the rotor frequency Fr is S times Fs, which is 1 by 3 minus 1 by 3 into 50 Hertz, which is minus 16.66 Hertz. So what does the negative frequency, negative slip mean? Take a situation that you have a vehicle to which the induction motor is connected, like in the locomotives, you have the train, and the train is moving uphill. So as the train is moving uphill, the MMF is moving at synchronous speed, and the shaft is trying to catch up with it, and it is motoring and it's pulling the train. And once the train has gone uphill and then it starts going downhill, the motor is also going to be aided by the gravity. So the motor is also going to rotate not only by the electrical energy that is being supplied, but also is going to get aided by the gravity. And if the gravitational acceleration is high, that is, the force due to the gravitational acceleration is high, then the shaft speed can go beyond the synchronous speed, in which case the mechanical energy, inertial energy which is there in the mass of the train is getting put back into the supply. That is, the power is, or energy is being is flowing from back into the mains, from the mechanical side to the electrical side. In such a case, the motor is acting like a generator, and then it is called an induction generator. So when the slip is negative, it means that it is acting like a generator, and that is the significance of the negative signs. It still means when you see the waveform on the scope, it will be just 16.66 Hertz, but the negative side only indicates that the energy is put back from the mechanical side to the electrical side. So this means that this is acting like a generator because of the negative side. So if we look at the axis that is the speed axis. And let me have let me tell you what that vertical axis is later, but for now let us say the x-axis is the speed axis that we have identified, and this is 0 speed, and somewhere here let us say is the synchronous speed. Now at standstill, when it is 0 speed, S is equal to 1, and at synchronous speed, what is slip equal to? Ns minus Ns by Ns, and that is S is equal to 0. So here S is between 0 and 1, 0 and 1. So S is having a value 0 here, gradually goes on to 1, and then it becomes greater than 1, yes, greater than 1. And then on this side, from 1 it has reduced to 0, and then starts becoming less than 1, less than 0, yes, less than 0. See, this is where the negative slip comes into the picture, and this is slip greater than 1. So when slip was greater than 1, we said that it is in the braking mode. So braking operation, the speed is negative, the other direction compared to the rotating magnetic field, and in the region which is beyond the synchronous speed, it is in the generating mode, acts as a generator, and in the region between 0 and synchronous speed, the motor behaves like a motor or the motoring mode. These are the three modes in the case of the induction motor. And if we look at the points on the x-axis, at standstill case 1, this was case 1 of the problem, S is equal to 1. Then somewhere at around this point, you have 500 RPM, and this point is case 2, and at 500 RPM we had the slip of 0. S is equal to 0.66, and then we had the point which was braking, which is greater than 1, a slip of greater than 1, let us say somewhere here, where you had rotating with minus 500 RPM, means counter if positive is counterclockwise, then the negative is clockwise direction of rotation, and here the slip S was equal to 1.33 braking, and the fourth operating condition was that the slip was negative. Somewhere here we had 2000 RPM, and we had the synchronous speed of 1500 RPM, and this was case 3, and this is case 4. and the slip here was negative minus 0.33. So these are the various operating points on the x-axis. The y-axis, we would like to see what is the torques at the various points as the speed evolves. We will look at that also. You got this concept clear? The various operating points, the various zones, operating zones of the induction motor. So now let us look at the same diagram . We have the speed and we have, let us say, the torque. So the motor torque generated, standstill, and somewhere here let us have the ns, synchronous speed. Now at standstill there is the rotating magnetic field which is rotating at synchronous speed. Then there is a large difference, there is a slip of 1, there is a large difference in the relative speeds between the rotor conductors and the rotating magnetic field. The currents induced in the rotor are also of 50 Hertz. Now at this point there is some starting torque that is generated to pull the motor out of standstill condition and make it to move. So actually the torque characteristic starts going like that and reaches some kind of a peak and then starts to fall like that. So the torque characteristic as it sees here, if you look at this point, you see the torque is 0 when the motor speed or the shaft speed is at synchronism with the rotating magnetic field, because there is no relative difference or the relative speed between the rotor conductors and the rotating magnetic field. There is no induction of the current in the rotor, and as a result there is no torque. That's what is shown here at this point. This is one crucial point. Now there is another crucial point here. This is called the maximum torque, Tmax, or the breakdown torque. Breakdown torque. Torque is in Newton meters, Nm. Now there is this torque, and this is called the starting torque, or also called the locked rotor torque, or also called the blocked rotor torque. And this point, of course, is a very small difference there. It is called the pull down torque. Slightly down, slightly lower than the starting torque, and that is called the pull down torque. So now if we extrapolate this into the braking zone, you will see that the torque continues in this direction, and in the generate, it is a mirror image. It starts coming like that and goes like that. So it will be a mirror image of what you see there. So this is in the generating zone. This is the braking zone. This is the braking zone. This is the generating zone, which is a mirror image of what is there in the motoring zone. So let us have a look at the torque characteristic a bit more in the motoring zone. Let us discuss it a bit more. So we have the motor torque, shaft torque, and we have the speed of the shaft. We have the speed of the shaft, and somewhere here we have ns, and at ns it has to become 0. So let us have the torque of the motor which goes like that, and then let us have it like that. Goes up there and then comes down. Let me make it a bit smoother here. Okay. So this is the torque characteristic of the motor. Now let me divide the torque characteristic into two portions. That is, this is the operating zone. So it is in this zone that the whole motor should operate, and the motor should very quickly go from starting into this zone of operation, because this is the stable zone. And this is the transient zone, and it is unstable. What does it mean by saying stable and unstable? Now let us say this is the torque that is generated by the motor. We call this as the torque, the red one. Okay, let me say that this red curve is the torque that is generated by the motor, generated by induction motor IM. Now let us see the load requirement. Let us say the load torque requirement. Let me give that in green, let us say. So let us say the load torque requirement is something like that. This is TL, load torque requirement, or that is required the motor. So which means that there are two possible operating points. There is one operating point which is here. There is also another operating point which is here. So let us take this operating point here. So let me call this as point 1, and let me call this as point 2. Now, due to some disturbance, let us say the operating point has shifted. So let us say the operating point has shifted slightly here. due to some disturbance, external disturbance, or change in parameters or whatever. So which means that here the speed what was rotating at nm is now going to be rotating at a speed that is much higher than nm, but the torque that is generated by the motor is lower than TL. So the motor is not able to supply the load torque here because of so much discrepancy in torque. So therefore the motor will try to stall and the speed will start coming down. As the speed starts coming down, the operating point shifts from here to this point again, which brings it back to the stable operating mode. Likewise, if the operating point had shifted here, the speed here is lower. The speed here is lower compared to the normal operating point nm, and the torque is higher. So because the higher torque, it tries to make the motor shaft move faster, and the speed increases, torque decreases till it comes back again to the operating point. So therefore, even if there is a slight deviation in the operating point, the characteristic is such that it pulls it back to the operating point to supply the load. Therefore, anywhere along this line here, what I am showing, that is in the operating zone portion of the line, they are all stable. Any deviations can be pulled back into the normal operating point for a given load torque. Now in the case of this zone, if there is any deviation, let us say here, from the operating point, the torque is higher, speed is higher, so therefore it will go still higher in speed and it will try to move away like this, away from the operating point. So it is not being brought back to the operating point. Likewise, if the operating point shifts here, the speed is lower, torque is lower, it is not sufficient to meet the load requirement, and therefore it will try to stall and the operating point still starts moving further away from the nominal operating point. So any disturbance will cause the system operating point to shift away from the nominal operating point where it is supposed to have been positioned. Therefore, anywhere in this region we should not position the operating point because that is the unstable zone. So it is important to note that we position our operating points only in this zone called the operating point zone. So that is very important. Now, there is one more important thing that happens to the torque characteristic with the change of some particular parameter, and this is where the wound rotor induction motor comes into picture and gives some useful insights. So let us say we have the torque and we have the shaft speed. And this is the torque in Newton meter. And we have somewhere here the synchronous speed. Let me first draw the characteristic curve. So we have something okay, so this is the torque speed curve where this point is ns. Now in the wound rotor induction motor, there is a possibility of introducing external, because the windings can, the current can flow through the external brushes. In the external circuit after the brush, we can introduce some impedance or resistance to create some additional features in the motor. Or if the motor is designed with a given, even in the squirrel cage induction motor, the resistance of the rotor conductors play a role on the torque speed characteristic. So let us see what happens if the resistance is increased, meaning if the resistance of the rotor conductors. So let us say this is at the nominal value. Now let us say on increasing the rotor conductor, resistance of the rotor conductor, the curve changes shape and starts going in this fashion. So you see that the peak torque, of course, is the same. This is T max. So this is, let us say, rotor resistance RR1. Now here RR2, which is greater than RR1. So what has happened here? Two things. We have a higher starting torque, and the maximum torque is the same. And third, the range, operating range, is much higher, meaning the operating speed range, if you look at the x-axis, is larger when compared to the operating speed range of the lower resistance motor. If I further keep increasing it, one could probably have a curve which is like that. So you see that the starting torque is still further brought up to the maximum. So this would be R3 greater than R2. On further increasing, you will see that this starting torque curve still goes lower. Now from there it starts going lower. So the torque characteristic can be modified, and the starting torque characteristic can also be modified. So we have starting torque increases as RR increases. Operating speed range increases as RR increases. Power dissipation in the rotor increases as RR increases, because now the RR, the rotor resistance, is higher, the I square R loss is going to be that much more higher, and as a consequence efficiency decreases. So therefore it is not advisable to permanently increase the rotor conductor resistance, because the efficiency will come down drastically. Therefore, in the case of the wound rotor induction motor, as the windings are brought out through the slip rings, through the external circuit we connect resistance. So during starting, the torque is pretty high. So you have a very high starting torque, very high starting pull. Now as the speed increases, you cut out the resistance, modify the torque characteristic such that it takes the form of that of the red line, and in the operating zone is narrowed and the efficiency becomes higher. Okay. So the operation characteristics can be modified that way. The torque speed characteristic can be suitably modified by including external resistance, which is possible only in the case of the slip ring or the wound rotor induction motor. So that is the way the torque speed characteristic looks like. There is just one more point that you need to know about the torque speed characteristic. What happens to the torque speed characteristic as the speed, the synchronous speed is changed? This is the shaft speed. It's the torque speed characteristic. So let us say, so we have a torque speed characteristic which is like that. Okay. This is at ns. Now let us say the new ns, this is ns1, this is ns2. New ns, the torque speed characteristic is actually parallel and starts and at ns3 the torque speed characteristic goes in a parallel manner and goes like that. So on, you will see a family of torque speed characteristic curves which goes like that. So the torque speed characteristic at different synchronous frequencies, because if the stator frequency is just 50 Hertz, then yes, this is the only torque speed characteristic. But the stator frequency changes, then we can have a series of torque speed characteristic which it's a family of curve as the frequency decreases. So here you see the frequency decreasing. Oh, sorry, the frequency is increasing like that. From 0, the frequency is increasing. This is very useful in the sense that when we want to do speed control of the induction motor, this kind of an approach is used. We will discuss about that later. Now let us have a look at how the active power flows through the machine. So the machine let us say to the machine we have the energy being input in the electrical domain, and we will call it as PS, as the power, stator power, which is put to the induction motor. So this is the power input to the stator, and the stator we will represent it as a circle. This is the stator, and in the stator, whatever power comes into the stator, there are some losses in the stator. What are these losses? So we could have some loss in the stator, P loss in the stator, which is due to I square R. That is, there is a stator coil, and the stator coil is made of copper, and that is having a finite resistance. So current is flowing through the resistance of the stator coil. Therefore, there has to be I square R loss. And the other thing, like in a transformer, we have the iron loss. the energy is transferred from the electrical domain to the magnetic domain through the core. The core is made of silicon steel, non-grain oriented silicon steel, and that is called the iron loss or the core loss. This is basically the core loss, and core loss can occur due to hysteresis or eddy currents like we discussed in the transformer. And then the remaining power, after all this gets subtracted, goes into the magnetic domain, and core loss component is removed, and then it goes into the rotor. So the rotor input power, we will call that one as PR. So the power input to the stator, PS, some amount from PS is removed and goes off as I square loss, the stator resistance and core loss, and the rotor, and the remaining power goes as PR into the rotor. And in the rotor also we have these two losses, P loss in the rotor. This is also I square R loss. That is, the rotors have conductors and the conductors are having finite resistance, and there is I square loss in the rotor. The rotor is also having core material, and therefore it also has its iron loss, and we will call that one as, we shall call it as the core losses. But what we could do is, we can club the iron losses of the rotor and the stator, because it is the same magnetic domain, and put it as a single core loss component. So what we will do, we will say that the loss after the power input to the rotor, a portion of it is lost in I square R. The iron loss comprises the total magnetic core loss, including the rotor and the stator. And then further, this goes as mechanical power PM. Now this mechanical power PM could get some portion lost here, as I will put the lost here as friction losses, because there could be friction in the bearings, and B square omega square B. So what would be is omega square into B would be the friction loss which you will see, and that finally the remaining power is actually P shaft, or the shaft power. So this is how the power flow diagram is in the case of the induction motor. So you have the stator power, which is PS, which is the input to the motor, that is the stator, and out of that a portion PLS goes off as the stator loss, I square R loss, and an amount PI goes as the core losses in the magnetic domain of the stator rotor. Then the remaining portion PR enters the rotor, and there is some amount which goes off as the copper loss, P loss or PLR, as I square loss due to the rotor resistance, conductor resistance. The remaining power goes as PM, and out of the PM an amount of power omega square B goes off as friction losses in the bearings, and the remaining power is the shaft power which is available to the load. This goes to load. So this is the active power flow diagram. We stop here at this point and continue in the next class. Thank you.